Do you wonder what this is about? A pendulum moving back and forth.
Be ready because today we're gonna talk about periodic motion.
motion. Hello
Hello
everyone.
everyone, we are the fourth group and we will bring the most fun out of this topic while you are learning. So just sit back and learn.
Before we start, we should know what periodic motion really is. A motion that repeats itself after equal intervals of time is known as periodic motion. For better understanding, a periodic motion can also be represented using oscillatory motion. What is oscillatory and what is oscillatory motion? An example is an object that oscillates about an equilibrium position due to restoring force or torque is said to be in an oscillatory motion. Wait. Didn't understand it at all. What is oscillate? What is equilibrium? And what is torque? When we say oscillate, it means to move or swing back and forth at a regular speed. The equilibrium is the point where the mass of the pendulum is located when it is not in motion, while the torque is the force that causes an object to rotate about an axis. But in our case, a pendulum only rotates partially on an axis and not fully. But what does that mean? Here is a better explanation for you to understand. In the beginning, we saw a pendulum swinging around back and forth. We can call it a simple pendulum. Now, a simple pendulum can be described as a device where its point of mass is attached to a light inextensible string and suspended from a fixed support.
Now here are the parts of a pendulum. The point of mass, which is the thing or object that is hanging, it is often represented by a round object or a ball. The inextensible string, meaning the string is not elastic or it cannot be stretched. The fixed support is where the string is attached from above. This simple device is the best example that demonstrates periodic motion or oscillatory motion because as the mass or ball moves back and forth, it takes a regular time interval before it goes back to its original position. Assuming that we are in a perfect universe, a frictionless one, a pendulum in motion will not stop swinging because it does not lose energy. In simple terms, it will swing forever until the end of time.
More definition of a simple pendulum. A simple pendulum is a mechanical arrangement that demonstrates periodic motion. The simple pendulum comprises a small bed of mass, represented by M, suspended by a thin string secured to a platform at its upper end of the length. The simple pendulum is a mechanical system that sways or moves in an oscillatory motion. This motion occurs in a vertical plane and is mainly driven by gravitational force. Interestingly, the bulb that is suspended at the end of the string is very light that somewhat we can say it is even massless. The period of simple pendulum can be extended by increasing the length of the string. However, it should be noted that if the mass of the bulb is changed, the period of time it takes to oscillate will remain unchanged. The period of time is influenced mainly by the position of the pendulum in relation to Earth as the strength of the gravitational field. Meanwhile, pendulums are a common system whose usage is seen in various instances. Some are used in clocks to keep track of the time, while some are just used for fun in case of a child swing. In some cases, it is used in an unconventional manner, such as a sinker on a fishing line.
These are the important things we must know about the periodic motion of a pendulum. The time, it is the interval or period of time it takes for the pendulum to swing back to its original position, and it is measured in seconds. The frequency, it is how often the bob of mass swings in 1 second. It is measured in Hz or Hertz. The mean position, it is the position where the pendulum has equal potential and kinetic energy. It is the middle part of the pendulum, and it can also be seen as a position where the bob of mass is when it is not in motion. The amplitude, it is the distance or displacement of the bob of mass from the mean position. Now, why is periodic motion often represented as a wave? But in reality, we never saw it happen. The waves, as a representation of periodic or oscillatory motion, are just a two-dimensional representation of the motion in a vertical plane. As we can see, the position of the bob changes over time, and if we graph it or we visualize it, we can see a wave-like pattern.
Another example where we can describe periodic motion is in a simple harmonic motion. But before that, we must know what it means. Simple harmonic motion can be described as an oscillatory motion in which the acceleration of the particle at any position is directly proportional to the displacement from the mean position. When we say directly proportional in this subject, it means that when the acceleration is increasing, the displacement from the mean position is also increasing, and vice versa. Here we have the spring mass system, which will show us the physical application of simple harmonic motion. Suppose we have a spring in a horizontal position. One end of the spring is attached to a wall, and the other end is attached to a ball. Assuming we are in a perfect universe, a frictionless one. Now, we have this setup. We can call this the equilibrium position of the ball. Theoretically, if we are in this perfect universe, when we pull or push the ball attached to the spring, it will never stop oscillating because there is no friction or external force hindering it to stop. In simple terms, it does not lose energy.
Now, the formula for the period of time it takes for the ball to complete one period or to move back and forth is T equals 2 pi times the square root of m over k. But what do these letters mean? T means the period of time it takes for the ball to move back and forth. M is the mass of the ball. K is the spring constant from Hooke's law, which we will talk about later. Where does this formula come from? As we said earlier, acceleration is directly proportional to the displacement of the ball from the mean position, so we can denote it as A is directly proportional to x position. We will use this property to derive the equation of time period. To start, we should write it as A is directly proportional to x and remove the sign of proportionality. In order to do that, we will write it as A is equals to a constant times x. In this case, we have a mass attached to a string and its constant is k over m, which came from Hooke's law. Now we will write it as A is equals to negative k over m times x. This will be our first equation. Now, because this formula is insufficient, we need another formula of constant of acceleration in terms of angular motion. This formula can be denoted as 4 pi squared over t squared. We will also substitute this equation in our property of simple harmonic motion, which is A equals constant times x, and it will be written as A equals negative 4 pi squared over t squared times x. We can call this our second equation. Now, we will combine these equations to derive the formula for the time period. We will write it as negative k over m times x equals to negative 4 pi squared over t squared times x. We will now cancel the x and the negative sign because both sides have it. It will become k over m equals 4 pi squared over t squared. And when we combine it, it will become t squared times k equals 4 pi squared times m. And to isolate the time period, we will have t squared equals 4 pi squared times m over k. We will square both sides to remove the exponent of t. Now we have t equals 2 pi times the square root of m over k. And that's how we derive the formula for the time period. This formula is just for the basic setup of spring mass system. There are other formulas for different combination of springs, and these are their formulas. They are also derived from our original property of simple harmonic motion and Hooke's law. For the time period in parallel combination, we have t equals 2 pi over w equals 2 pi times the square root of m over kp equals 2 pi times the square root of m over k1 plus k2. For the time period in series combination, we have t equals 2 pi times the square root of m over ks equals 2 pi times the square root of m times k1 plus k2 over k1 times k2. The spring constant that we mentioned earlier is from Hooke's law, which is a law of physics that states that the force needed to extend or compress a spring by some distance scales linearly with respect to that distance. That is, F equals kx, where k is a constant factor characteristic of the spring and x is compared to the total possible deformation of the spring.
Now here is the truth. Did you know that all those explanations and formulas are only applicable in the perfect universe, a frictionless one? We will go back to our pendulum. And in reality, a pendulum will not return to its original amplitude over time, and it will eventually stop. But why do pendulums stop? The answer lies in the lesson about thermodynamics. However, in this lesson, we will call it damping. But what is damping? Damping is an influence within or upon an oscillatory system that has the effect of reducing or preventing its oscillation. In simple terms, damping is the gradual dissipation of energy, and the result is for the pendulum to stop. The energy does not just magically disappear. According to the first law of thermodynamics, energy can neither be created nor destroyed, only altered in form. The dissipated energy from our pendulum is dissipated into heat by the process of friction. This happens on the ball while it is experiencing air resistance and to the point where the string is attached. There are three types of damping or damping system: the underdamp, critically damp, and overdamp. If the instrument is underdamped, the moving system will oscillate about the final steady position with a decreasing amplitude and will take some time before it comes to rest. But when the moving system moves rapidly but smoothly to its final steady position, the instrument is said to be critically damped or deadbeat. While if the damping material is more than what is required for critical damping, the instrument is said to be overdamped. We can visualize these three in this video. We can see damping systems in physical application in a high-rise building, and they are called dampers. This is to reduce the swaying of the building when it is hit by strong winds. Again, periodic motion is a motion that repeats itself after equal intervals of time.
Today we learned about periodic motion, oscillatory motion, simple harmonic motion, and damping system,
and what is its application.
We
We
are
are the
the fourth
fourth group,
group and we hope you learned something.
something.